Intermolecular forces. They are forces that attract or repel neighboring particles, so atoms, molecules, or ions. They are weaker than intramolecular forces. London dispersion is one of these forces. It is the weakest attractive force between molecules. All matter experiences London dispersion. It is when the nucleus of an atom is attracted to the electrons of the other atom in a molecule. So, nucleus 1 is attracted to nucleus 2. An induced dipole, which is what the example above is created when two molecules are in the presence of one another. A dipole is just the separation of charges within a molecule between two covalently bonded atoms. In order to show that a molecule is going through London dispersion forces, we must first understand polarity. A polar molecule is a molecule that contains a distinct positive and negative region due to the presence of polar bonds. For example, H2O. So first we have to find out what hydrogen and oxygen's electronegativity is, and we can find that on the periodic table here. So hydrogen's electronegativity is 2.2 and oxygen's is 3.4. And electronegativity is just the measure of an atom's tendency to attract the bonding electrons of another atom. So oxygen has a higher electronegativity than hydrogen. Therefore, hydrogen's bonding electrons are more attracted to oxygen's, and we show it with these arrows. Because hydrogen is sharing its electrons, it gets a positive charge, and oxygen gets a negative charge. You can see that there is a distinct negative and positive region. That means this particle is polar. We just show it with an arrow like that. So this region is negative, and this region is positive. When a molecule does not have a clear positive and negative region, it is nonpolar, but it will contain polar bonds if each atom has a different electronegativity. For example, CH4, and that's how it's drawn. So hydrogen's electrons are attracted to carbon's. And you can see that all around carbon is negative, have positive charges. And then carbon has a negative charge. And there is no distinct positive and negative region. So it's nonpolar. What impact does London dispersion have on physical properties? The answer to this is boiling or melting point. This is because the higher the difference in electronegativity, the stronger the bonds between each atom. For example, carbon dioxide and water. Carbon's electronegativity is 2.6. Oxygen's is 3.4. 3.4 minus 2.6 is 0.8. So that's their difference in electronegativity. You do the same thing with water, and you find that hydrogen and oxygen's difference in electronegativity is 1.2. Therefore, water has stronger bonds and is harder to break apart. So, water has a higher boiling point than carbon dioxide. What affects the strength of London dispersion forces? First, size. The larger the molecule, the stronger the London dispersion forces. Remember, size is determined by the number of protons and electrons in an atom. For example, CH4 versus C3H8. CH4 has 10 protons, and C3H8 has 26 protons. So CH4 has 10 electrons, and C3H8 has 26 electrons. Therefore, C3H8 is bigger, so therefore it has stronger London dispersion forces, and therefore a higher boiling point. Secondly, their shape. The greater the surface area contact, the higher the London dispersion force. Therefore, the greater the surface area contact, the higher the boiling or melting point. For example, So this shape has a larger surface area than this shape. So this means that this shape has a higher London dispersion force than this one. So this one has a higher boiling or melting point than this one.
In the second part of this video, we'll be talking about dipole-dipole interactions. A dipole-dipole interaction comes into play when you have two molecules that are polar, for example, FCH3. One side is negative and the other side is positive, creating poles. When a second molecule is introduced, the poles like to line up and connect to each other, positive to negative and negative to positive. This creates a strong attraction between the two, stronger than London dispersion forces. The strength of a dipole-dipole interaction comes from the electronegativity differences within and between the molecules. The bigger the difference between the two molecules, the stronger the interaction is between them. The properties of a dipole-dipole interaction include the boiling and melting points. The boiling and melting point of a substance changes depending on its dipole-dipole interaction, or any of the interactions for that matter. But the presence of dipole-dipole interactions increases the boiling and melting point. And the stronger the dipole-dipole interaction is, the higher the boiling and melting point is. The second property of dipole-dipole forces is the solubility. We use the term like dissolves like. For example, a polar molecule will dissolve a polar molecule, and a nonpolar molecule will dissolve a nonpolar molecule. However, a polar and a nonpolar molecule will not dissolve into each other. Like dissolves like. In the next part of this video, we will be talking about hydrogen bonds. Hydrogen bonds are a special case of dipole-dipole bonding, which means dipole-dipole bonding must occur before hydrogen bonding can occur. Hydrogen bonding occurs when hydrogen bonds in the same material with one of three things: oxygen, nitrogen, or fluorine. However, it is only considered a hydrogen bond when hydrogen is alone with fluorine, if fluorine is the atom in question, the element in question. For example, nitrogen and hydrogen bond together, and that creates a hydrogen bond. However, hydrogen bonded to a carbon bonded to a fluorine is not, because there's a carbon in the equation. If you take the carbon out and just have fluorine and hydrogen, it creates a hydrogen bond. The strengths of a hydrogen bond depend on how many oxygens are in the equation, or how many bonds can be made within this hydrogen bond. The more oxygens that are in the equation, the more hydrogen bonds that can be made. For example, if oxygen is bonded to a hydrogen, bonded to another oxygen, this would have two opportunities for hydrogen bonding, whereas oxygen bonded to a hydrogen would only have one opportunity for hydrogen bonding with another molecule, meaning O2H has a better has a stronger hydrogen bond than just OH.